Hi everyone, I'm Li Jie from Tianjin University. I'm glad to introduce our work Tetris, Memory Efficient Serverless Inference through Tensor Sharing. This work was conducted by Tianjin University together with Wuba.com, a large local life website in China. Serverless computing is becoming more and more popular in recent years due to its ease of use, cost efficiency, resource management free, and auto-scaling advantages. Serverless inference, or in other words, deploying machine learning or deep learning inference services atop a serverless platform, is becoming popular in the IoT, mobile, and web applications. However, as we have found, the current serverless inference platforms are highly memory inefficient. Here is a sample overview of a serverless inference system, where client forward the inference requests to the remote service over the network, and in the backend, multiple function instances will be spawned to do the inference. And inside each function instance, there is a machine learning model with trained parameters that should be loaded into memory before the computation. First, the workload towards online ML inference is high. For example, there are tens of trillions inferences per day in Facebook. With so many requests, the serverless platform will scale out a huge number of instances according to its auto-scaling nature. Moreover, machine learning, especially deep learning applications, typically require the loading of enormous parameters, which is memory consuming. For example, the universal sentence encoder model, which has been downloaded 1.4 million times on the TensorFlow hub and consumes 1.72 gigabytes of memory at runtime. Eventually, with such a vast number of instances and such a high memory consumption per instance, the system's memory resources will be extensively harvested. And as far as we know, previous works of the serverless inference systems mainly focused on computational resources like CPU and GPUs, while paying less attention to the memory resources. The root cause of memory inefficiency is the large amount of data redundancy in memory, which is caused by first, the multi-instance nature of serverless platforms. For example, AWS Lambda creates new instances for each request if there is no existing warm instances. And since instances are isolated with sandbox, data like the model parameters are required to be loaded repeatedly into the memory. Second, the early provisioning and long keep-aliving of function instances to reduce cold starts. For example, function instances would be pre-launched or kept alive for 15 to 16 minutes after execution in AWS Lambda, which is much more longer than the inference computation time. And although these idle instances consume less CPU power, they do consume memory. And in this work, we are trying to reduce the high memory redundancy and improve memory efficiency. And to solve the problem, previous works have proposed the runtime sharing method, or in other words, packing multiple requests into a single instance to share the runtimes. For example, grouping and processing requests in a batch or process requests concurrently with multiple threads. With such methods, the number of launched instances could be reduced so that the memory consumption could be reduced. However, we further observed that even with runtime sharing, the parameter tensors are still redundant across either instance of the same function and the instance of different functions. Machine learning models are typically implemented with specific frameworks, and in these frameworks, models are typically represented as computational graphs, and data in the graph are stored as tensors. And here is a simple example computational graph in TensorFlow. Since model parameters stay unchanged during inference, it is easy to find out that the parameterized tensors are redundant across function instances. Moreover, these parameterized tensors typically consume the bulk of memory during the inference. For example, for a VGG19 inference process, storing the model parameters accounts for more than 93% of the total memory consumption. Moreover, we also noticed that parameterized tensors would also be identical across different functions. For example, for model pipelines, which refers to a pipeline that contains specific pre- and post-process operations, or a pipeline of multiple models. Different functions may deploy different pipelines, and these pipelines may include identical models. Moreover, pre-training and transfer learning are popular techniques and is widely used in practice. And in the process of pre-training and transfer learning, it is also common to only retrain a subset of parameters in case of similar downstream tasks or insufficient training samples to reduce training costs and improve accuracy, which also causes different functions to have identical tensors. For example, here is an illustration of ResNet 50. And when we only retrain the last fully connected layers, the parameters in previous convolutional layers could be identical across different functions. To summarize, our main contributions are first, an observation of the tensor redundancy problem in serverless inference platforms. And second, to solve the problem, we proposed a lightweight and user-space memory mapping solution that automatically shares identical parameterized tensors across function instances. To improve the memory efficiency, we carry out Tetris, which eliminates the high data redundancy with tensor sharing, and also along with runtime sharing. Here is an illustration of the overall architecture of Tetris, which enables runtime sharing through its scaling and scheduling engine, and supports tensor sharing through the agent in each container, and the tensor store on each server. And as an overview, Tetris improves memory efficiency in 3 steps. First, Tetris shares tensor memory of function instances that are co-located on the same server. Second, Tetris carefully schedules function instances to dedicated servers to share more tensor memory. Third, Tetris also supports runtime sharing, which aims at scaling fewer function instances to serve requests under the service-level objective constraints. So the first question is how to share tensors of function instances on the same server. And to start, we make a shared memory region across function instances, which is implemented by mounting a shared template phase to each container. Second, we take over the model loading process of function instances and put tensors into the shared region. Third, we make sure that tensors in the shared region are reclaimed correctly. So the main process of tensor sharing is done by the agent. The agent first parses the computational graph of the model and finds out the parameterized tensors to be loaded. And for each tensor, it checks if it is already existing in the tensor store. If no, the agent allocates a new memory region in the tensor store, then reads and fills in the parameters. If yes, the agent just reuses an existing memory region through the mmap system call. And we use logs to synchronize between concurrent agents. And to identify if the tensor has already been loaded, we adopt hash values, since the hash values are computed only based on the tensor contents. The process of tensor sharing still works across different machine learning frameworks. After the tensors are shared, they may be referenced by different instances. It is also important to detect and reclaim the unreferenced tensors correctly. To achieve this, we deploy a separated reclaimer on each server and run a detection and reclaim loop periodically. Inside the loop, the reclaimer first retrieves the set of referencing tensors denoted by T1, then gets the tensor set reside in the tensor store denoted by TO, and finally, the tensor set to be reclaimed is inferred by TO minus T1. And since we have also observed that the loading of massive model parameters dominates the startup process of function instances, and tensor memory mapping is far faster than loading and decoding tensors from disk. The reclaimer also supports keeping alive the unreferenced tensors to accelerate function instance startups in the short future. To sum it up, the tensors first loaded from the model file by the agent, then may be memory mapped by other instances. And when the reclaimer detects that no function instance is referencing, the tensor memory can either be reclaimed immediately or kept alive. Our design does not support sharing of tensors across servers due to frequent tensor access during inference and the high network latency. Instead, we maintain a shared tensor store on each server for performance guarantee, while minimizing cluster memory consumption through instance scheduling. We employ a simple greedy algorithm in which we always try to schedule instances to the server with the maximum tensor similarity. And the basic idea is that we want to share as many tensor memory as we can after the scheduling. Moreover, for runtime sharing, although previous works have indicated that it can be implemented through batching or multi-threading, we observed that the different combinations of batch size and concurrency lead to different memory efficiency. So in Tetris, the runtime sharing is implemented with a combination of batching and multi-threading. And the same as in previous inference systems, we also support the SLO constraints. And specifically, for each function, we profile its latency under various configurations and then model the instance scaling process as an optimization problem. The scaling engine monitors the real-time RPS and judges whether the existing instances are sufficient to serve these requests. If no, it dispatches parts of requests to existing instances and launch new instances to process the residual ones. The subject of the optimization problem is to minimize the memory consumption of the newly spawned instances, and the constraints ensures that the SLOs are guaranteed and the residual IPS can be fully processed by the newly spawned instances. However, this optimization problem can be reduced to the NP-complete knapsack problem. So we developed a simple greedy solution for which we greedily select configurations with the maximum normalized throughput. And this method can also be easily extended to balance CPU consumption by normalizing the throughput with a linear combination of memory and CPUs. To evaluate our system, we collected 21 inference models from both TensorFlow Hub and the local lab website, ranging in model sizes from 11 megabytes to 3.5 gigabytes, vary in download times from 310 to 1.1 million, and covering application domains including text, image, audio, etc. Our testbed contains 8 servers, two servers are equipped with 80 cores and 256 gigabytes of memory, while 6 others are equipped with 32 cores and 128 gigabytes of memory. This figure here shows that the memory reduction under different number of function instances with tensor sharing. Here we compare the memory consumption of all launched instances with or without tensor sharing. And for the USE model, when deploy 32 instances, the memory reduction exceeds 93%. With tensor sharing, the memory consumption has been extensively reduced. More function instances could be deployed. And for the USE model, consider the 256 gigabytes machine memory capacity. The function density would be improved by up to 30 times. Since the tensors can be shared with direct memory mapping, the time-consuming model loading process can be accelerated. And for example, for the VGG19 model, compared with loading the entire model from disk, the function startup can be accelerated by up to 91.56%. With such a large reduction in memory consumption, we also measure the inference latency of various ML models and compare the latency CTF with or without tensor sharing, and find that our memory mapping method does not introduce latency overhead. Furthermore, to evaluate the overall performance of Tetris, we adopt 4 real-world applications and 3 real-world workload traces collected from Microsoft, and we compare to Inferless, which supports runtime sharing with request batching, and Photons, which supports runtime sharing with processing requests concurrently in threads. And we also compare to a runtime sharing only version of Tetris. So the Photons is not serverless inference oriented. We modify it to our scenarios by adding function profiles and greatly selecting instance configurations with the maximum concurrency under SLO constraints when scaling instances. The result shows that Tetris achieves the lowest memory consumption, which is because first, with tensor sharing, Tetris can further reduce the tensor redundancy across either the instances of the same function or across different functions. Second, the combined runtime sharing method in Tetris also ensures that we can pack more requests to share the runtime of a single instance, so to spoon fewer instances to accommodate the requests, thus also consuming less memory. And specifically, when considering the second-hand vehicle trading application under a stable load, Tetris can reduce the overall memory consumption by more than 86% compared with Inferless, which is the state-of-the-art serverless inference system. To conclude, Tetris is a memory-efficient serverless inference system, which is easy to implement, transparent to users, and require no modifications to the ML models. It also does not hurt the inference performance, and we think both developers and cloud providers would benefit from Tetris due to its startup acceleration and high memory efficiency. Thanks for listening.